Welcome to this course on Prophet, the time series forecasting library developed by Meta. If you are looking to make accurate predictions without the pain of complex setups, you are in the right place. In this video, you will learn how to set up a basic Prophet model, to generate a forecast, to extract and visualize time series components, and to evaluate a Prophet model's accuracy, all using Prophet built-in tools and therefore a few lines of code. So what exactly is Prophet? Prophet is an open source forecasting library built by Meta. It's designed to handle seasonal data, missing values, and trends with minimal effort. Unlike traditional forecasting models like ARIMA, Prophet is designed to be easy to use, no need to manually fine-tune parameters, interpretable, you can easily understand the trend and seasonality components, and resistant to outliers. It handles missing data and sudden spikes better than most models. Next, let's look at how Prophet actually works. Prophet is based on a concept called time series decomposition. This means it breaks your data down into three key components. First, the trend. This is the long-term decrease or increase in your data. Second, the seasonality. This refers to repeating patterns in your data. If sales are higher on weekends or during the holiday season, for instance, Prophet automatically detects these patterns. Finally, the holidays or events. Those are special days like Black Friday, Christmas, or even unexpected spikes that can be included in the model. Prophet then projects them into the future and creates confidence intervals to account for uncertainty in predictions. The result? A flexible and interpretable forecast that adapts well to real-world business scenarios. Now that we know how Prophet works, let's see what inputs it requires and what output it gives us. To use Prophet, you only need two columns in your dataset. DS, the date, this should be in standard datetime format, and Y, the target variable, the value you want to predict, like sales, web traffic, or demand. When Prophet generates a forecast, it gives us Y hat, the predicted value, Y hat lower, and Y hat upper. These are confidence intervals helping us understand the range of possible values. You can also add extra input like holidays and external regressors, but these are out of the scope of this first video. Now that we understand the basics, why should you use Prophet? Let's see how Prophet compares to other forecasting methods. Amongst Prophet advantages, the first one is the ease of use. Unlike ARIMA or machine learning models, Prophet requires minimal setup. It also handles missing data, so if you have gaps in your data, Prophet can handle it as opposed to machine learning models. Finally, it's based on time series decomposition and therefore is explainable, making it great for business forecasting. On the other hand, Prophet isn't great for very short time series. Why? Because Prophet relies on time series decomposition, and that means it needs multiple seasonal cycles to properly extract patterns. With too little data, it just can't detect seasonality well. In those cases, ARIMA or exponential smoothing often perform better. Then Prophet also struggles with highly nonlinear relationships. It assumes that effects, like holidays or promotions, are additive or linear, but real-world data often isn't that simple. If your data has sharp spikes, sudden dips, or complex interactions, models like XGBoost or neural networks are better equipped to handle that. Finally, Prophet falls short for long-term forecasts. It's great at modeling recent trends, but it doesn't remember long-range dependencies. For forecasts that stretch far into the future, models like LSTMs do a much better job by learning from earlier context in the data. Bottom line, Prophet is great for fast, interpretable forecasting, but it's not a one-size-fits-all, so always choose your model based on your data and your forecasting goals. Before we start, let's make sure you have everything set up correctly. To follow along, you'll need basic Python knowledge, no advanced statistics required, a code editor, and Python installed on your computer. Before we dive into the coding section, let me quickly introduce the dataset we'll be working with and a GitHub repo I've prepared. First, the dataset we'll be using is a dataset from Kaggle that contains historical data of daily minimum temperatures. Next, the GitHub repo contains all the code from this tutorial along with any additional resources you might need, including the Kaggle dataset. Alright, now that you have everything you need, let's get started with the coding. Let's start by creating a virtual environment. This will avoid conflict between packages and keep our setup clean. To do so, let's open a new terminal and write python 3-make virtual environment, and let's call it my virtual environment. If everything went well, you should see your virtual environment folder created in your project folder. Now, let's activate our virtual environment using source, my virtual environment, bin, and activate. Let's now install the required dependencies, so let's write pip install -r requirements.txt. Here we will simply go through the requirements files and install the associated dependencies. While the dependencies are installing, let's create a notebook and call it forecasting with Prophet. Now that the dependencies have successfully been installed, let's have a look at how the data that we are going to work with is structured. Let's go in the data folder and open the CSV file. Here we see the data structured in two columns. First, a column date, and second, a column containing temperatures in degrees Celsius. Let's come back to our notebook and import the data into a data frame. So let's start by importing pandas as PD. Let's create a new section, load the data, specify the path of the file, which is located in the data folder and named daily minimum temperatures.csv. Let's create a new data frame indicating that the date column contains datetime values. Let's simplify the column names using temperatures.rename and provide a new mapping to have data in lowercase and temp instead of daily minimum temperatures. Let's now display the first 5 rows of our data frame and check the output. Nice, so we have successfully loaded our data. The next step is to visualize this data. So let's import matplotlib.pyplot as plt, create a figure of size 12 by 6 inches, and plot our data frame. For the x-axis, let's input the date, and for the y-axis, the temperatures. Let's provide a line style and label the curve temperatures. We'll give a label to our x-axis, date, and our y-axis, temperatures in degrees Celsius. Let's give our chart a title and call it temperature over time. We can also add a grid to the plot by setting grid to true. And finally, let's show the plot. First observation, there is an issue with the data reading. This might be driven by the type of data automatically detected in the data frame. So let's check by printing the type of data contained in this data frame. We see that the date column contains datetime as expected. However, the column temp contains objects where we were expecting floats. This means that the temperatures data is not read properly. To keep it simple, let's just convert the data into numerical values using pandas toNumeric function. In case of errors, the coes argument will input not a number values. Hopefully, the curve will look much cleaner. Nice. Here we have a time series over a 10-year time range. And the first observation we can make is that there is a flat trend across the period. This makes sense given that 10 years is a short period to observe significant and persistent climate changes. Second observation, there is a strong yearly seasonal pattern consistent with temperatures peaking in summer and dropping in winter, corresponding to natural seasonal cycles. Finally, we can notice that temperatures are rising around February and dropping around July and August, indicating that these measures were made in the southern hemisphere. So far, we have explored our dataset. Now it's time to create a basic forecasting model using Prophet. Let's create a new code cell and import Prophet from the Prophet library. Let's initialize a basic Prophet model. And as discussed in the intro, Prophet has input requirements, therefore we need to rename our columns using DS for the dates and Y for the target variable, in our case the temperatures. Let's sort our data frame by dates. As a next step, we will split our data frame into a training and a test set. This step is optional, but will enable us to pilot and assess the accuracy of our model on unseen data. We start by defining a forecast horizon. In this case, let's put 30 days. We then need to split our data frame into a test set containing the last 30 days of data and a training set containing all the remaining data. To do so, I'm going to use a mask that I'll call here isInTestSet. To keep it simple, this is an array of Boolean values that will be equal to true when the date belongs to the last 30 days and false otherwise. Using this mask, we can now create the test set, keeping only rows for which isInTestSet equals true. The training set, on the other hand, corresponds to rows for which isInTestSet equals false. So let's put the not symbol in front of isTestSet. Let's display our training and test set. As expected, we have two consecutive data frames. The training set that ends on the 30th of November 1990 and the test set that starts one day later on the 1st of December 1990. We can now train our model. Let's create a new section and write basic Prophet model.fit temperatures train. Next step is to generate a data frame containing all the dates for which we want to make predictions. For this, we will use an out-of-the-box function from Prophet called makeFutureDataFrame. Let's set the periods argument to forecast horizon and the frequency argument to days. This will generate a data frame containing the dates of the training set plus 30 days forward, covering the test horizon. We can now make predictions. Let's use a variable called temperatures forecast to store the forecast that we can now generate using basic Prophet model.predictFuture. Now we might want to plot our forecast, so to do so we can use another out-of-the-box Prophet function. So let's create a variable forecast plot and generate the plot using basic Prophet model.plot temperatures forecast. Let's also visualize the time series components that Prophet computed to build the forecast. To do so, we can use the plot components function built in Prophet. Now let's see what we get. Alright, the 30-day forecast horizon is too small compared to the total range of data to properly visualize the forecast. So for the purpose of this video, let's increase the forecast horizon to 6 months. Let's also display our future data frame and our temperatures forecast data frame. Looking at the future data frame, we see that it indeed contains all the dates starting from the beginning of the training set until the end of the test set, covering the entire time range of the initial temperatures data frame. Now looking at the temperatures forecast data frame, we see multiple columns. The first one contains the target dates. Next, we have the trend, the long-term variations in the data, on top of which we will add the seasonal components. We then have y-hat lower and y-hat upper, corresponding to the confidence interval of the predictions. Since we did not specify any argument, the model is using a default confidence level of 80%. We have prediction bounds for all the time series components. Then we have the additive term. By default, Prophet is set to use an additive model. In this case, the model will use the additive term to summarize the seasonal effects. For example, here the additive term is 3.4 degrees Celsius, corresponding to the sum of the weekly seasonal component at 0 degrees Celsius and the yearly seasonal component at 3.4 degrees Celsius. As Prophet is set to additive, it does not use the multiplicative term. Finally, we have y-hat, our prediction, corresponding to the sum of the trend component and the additive term. In case of a multiplicative model, y-hat would have been the product of the trend and the multiplicative term. Now let's have a look at the Prophet forecast plot. On this plot, we see black dots corresponding to actuals or historical data. We also see a blue line corresponding to the forecast and a light blue shaded area corresponding to the confidence interval. Next, we have the time series components. Looking at the weekly seasonality, we observe small variations ranging from minus 0.15 to plus 0.1 degrees Celsius. These variations are relatively small, around 1%, compared to the overall average temperatures at 11 degrees Celsius. As there is no natural reason explaining a weekly seasonality in daily minimum temperatures, we can assume that there is no weekly seasonal component and that the Prophet model is overfitting. For low temperatures, around 1 degree Celsius, this could drive up to a 10% relative error. In this case, we would benefit from explicitly tailing the model not to capture any weekly seasonality. On the other hand, the yearly seasonal component is much stronger, from minus 4 degrees to plus 4 degrees, and plays a crucial role in the forecast. We indeed see that Prophet effectively captures the repeating peaks and troughs corresponding to natural temperature seasonal cycles. In this case, keeping the yearly seasonal component is essential. So far, we have loaded and formatted our data, split our data frame into a training and a test set, creating a basic Prophet model, and generated a forecast. Now, to decide whether we can use this forecast or not, we need to assess its accuracy. So let's start by backtesting our model using cross-validation. For this purpose, Prophet provides a built-in cross-validation function. So let's import it from prophet.diagnostics. Let's create a variable in which we will store the cross-validation output. This function takes multiple arguments, including model, horizon, initial, and period. Model is the trained Prophet model that we want to evaluate. Here we'll use basic Prophet model. Horizon corresponds to the forecast horizon. Let's input a formatted string containing the forecast horizon and the unit, here days. Initial indicates the minimum amount of historical data used to train the model in the first cross-validation iteration. Here let's input a formatted string containing 7 years or 7 times 365 days. Finally, period indicates the spacing between cutoff dates when creating validation points. Let's give a period of 15 days. This means that the first iteration of the cross-validation will use a training period of 7 years. The second iteration will use a training period of 7 years, extended by 15 days, and produce a forecast for the following 6 months, corresponding to our forecast horizon. We can now run our cross-validation. Now that the cross-validation is complete, we can compute accuracy metrics such as MAPE, mean absolute percentage error, or root mean squared error. For the error metrics computation, Prophet provides another built-in function. So let's import it from Prophet Diagnostics, import performance metrics. Let's create a new variable and call the performance metrics function. This function takes 2 arguments, the cross-validation data frame, and a rolling window that we will set to 0 for now. Let's now display the accuracy metrics. Here, the output shows Prophet accuracy metrics for different forecast horizons, going from 1 to 180 days ahead. This covers the entire forecast horizon. Each column summarizes the model performance for different standard accuracy metrics, such as the root mean squared error, the mean absolute percentage error, and the coverage. The coverage corresponds to the proportion of occurrences where the actuals fell within the confidence interval. Now let's come back to the rolling window parameter. This parameter helps smooth the accuracy metrics over different forecast horizons. With the rolling window set at 0, each step or day in the horizon has its own metric. We thus have a day-by-day accuracy report. If we set this parameter to 0.1 or 10%, Prophet averages metrics using a trailing window, which length corresponds to 10% of the forecast horizon length. In this case, the forecast horizon is 180 days long, so setting the trailing window to 0.1 would average the accuracy metrics using an 18-day trailing average. To get the performance of the model over the entire period, we therefore can set the rolling window to 1. For instance, here we get one single metric corresponding to the average performance of the model over the entire period. In short, the rolling window parameter controls the trade-off between detail and smoothness when reporting the forecast performance metrics. Let's revert the rolling window to 0. To visualize how an accuracy metric evolves as we go farther in the horizon, we can use another Prophet built-in function. So let's import it from prophet.plot, import plot cross-validation metric. Let's now call the plot cross-validation metric function and pass it a cross-validation data frame, a rolling window of 0, and choose the accuracy metric to plot. Here we'll plot the root mean squared error. Let's see what we get. On this plot, the y-axis corresponds to the accuracy metric, while the x-axis corresponds to the different forecasting steps in the horizon. This plot shows remarkably stable root mean squared error values, around 2.5 to 3 degrees Celsius, across the entire 180-day horizon. This reflects the inherently predictable nature of temperature data with its strong seasonal patterns. The consistent forecast performance, regardless of horizon distance, confirms that the model correctly captures the dominant yearly seasonality from -4 to +4 degrees Celsius. The subtle wave-like oscillation in the error matrix is likely driven by the inclusion of a weekly seasonal component, which represents overfitting since there is no meteorological basis for weekly patterns in minimum temperatures. Finally, the spread of individual errors, gray dots, likely represents weather anomalies and extreme events that naturally deviate from seasonal patterns. Disabling the weekly seasonality parameter would be a simple yet powerful improvement to reduce these cyclic error patterns and sharpen the model accuracy. This will be included in the scope of the next video, in which we will explore how to fine-tune a Prophet model by removing irrelevant components and incorporating features like holidays, events, external regressors to take your forecast to the next level. If you found this helpful, don't forget to like the video, subscribe and hit the bell icon so that you don't miss what's coming next. If you got any questions or ideas, feel free to drop them in the comments. I'd love to hear what you guys are forecasting. Thanks for watching, and I'll see you in the next one.